Okay, so as I was saying before, nice to meet you. My name is Federico Castelletti from Università Cattolica, Department of Statistical Sciences. Just as a few information, my main research interests are mostly Bayesian graphical modeling, which will be also one of the topics that we will cover today's afternoon. And then besides this, I also do research on causal inference, still using graphical models as a framework, and even causal discovery from, let's say, mixtures of observational experimental data, which are however, topics which will not be covered throughout this course. Okay, so what about the contents of today's module? So in the first session, so this one, we will introduce Gaussian graphical models. And to this end, we will also do a brief overview, a brief review, say, of multivariate normal models and normal linear regression, okay? While in the second session, we will consider frequentist approaches to structural learning, at least some frequentist approaches. Of course, there are many, there are a lot of different approaches. While this afternoon, we will talk about some Bayesian structural learning approaches. And then in the last session, we will do some practical, say, real data analysis. Okay, what about the resources? I will use a set of slides that are already available, and so that you can download them on your laptops, and then as well as our codes, which are already provided in our shared folder. And then I will give you some references, both textbooks or some papers that are reported at the end of each set of slides. Okay, so let's start from multivariate normal distributions. The reason why we need multivariate normal distributions is that, as we will see, Gaussian graphical models are, in a sense, an extension of a generalization of multivariate normal distributions in the case where the covariance matrix is constrained by a graph. Okay, so first of all, we need to review some results on multivariate normal distributions. Okay, also to fix the notation that we will use throughout our lectures. Okay, so we can start by considering a random vector, x1, xq. So q, random variables, if you like, for which we assume that they have a multivariate normal distribution with parameters which are a mean vector, say mu, and a variance covariance matrix sigma. Okay, in which case we write that x1, xq, given mu and sigma, if you like this kind of notation, which is the usual Bayesian notation, okay, where we condition on the parameter, is normal q, mu, and sigma. Ok, no, il problema è che se lo tengo qui non... Se lo tengo qui dicono che si sente un po' poco. Dovrei tenerlo più vicino alla... Ma non è un problema, davvero non è assolutamente un problema. Posso fare... Davvero, dopo al massimo nella pausa. Ok. Okay, where mu is our mean vector with components mu1, mu-q, and sigma is the variance covariance matrix with the diagonal entries corresponding to the variances and the out diagonal entries corresponding to the covariances between each pair of random variables. Okay, so in this case, if x1, xq has a multivariate normal distribution, then its probability density function is given by the expression which is reported here, okay, which depends on two parameters, which are mu and sigma. Okay, so you are, I think you are familiar with this kind of probability density function, right? Okay, so sometimes, and this will be the case in the next, we can use instead of sigma the inverse of sigma, which we can call mu. Sorry, which we can call omega. And it is the so-called precision matrix, okay? So in this case, we can write the PDF of a multivariate normal distribution in this way here, which depends on the determinant of omega, and then we have the exponential of our quadratic form, x minus mu prime omega x minus mu, okay? Okay, so now there are a few properties of multivariate normal distributions which are quite useful in particular when dealing with Gaussian graphical models. Okay, are related to marginalization and conditioning in multivariate normal distributions. Okay, so let's start by assuming that X, our random vector, has a normal Q mu sigma distribution. Okay, so multivariate normal, and consider a partition of 1Q into two sets, okay, A and B. Okay, so that we can consider X, A, X, B, which are the corresponding sub-vectors of X1, XQ. Okay, so vectors containing the components indexed by A and B in our random vector, called X. And so we can also partition mu, sigma, and omega as follows. So in particular, we have mu, which is, again, our mean vector with two components now, mu A and mu B. While for both sigma and omega, we can partition them into 4 blocks. 2 are diagonal blocks, like sigma AA, sigma BB. And the other 2 blocks are one the symmetric of the other one, of course, because both matrices are symmetric. Okay, and these are sigma BA, sigma AB. So the block of sigma with rows indexed by B, for example, and columns indexed by A. Okay, and we can do the same for omega, okay, in this way. Okay, so a first property of multivariate normal distribution is that the distribution is closed under marginalization, meaning that if we consider the marginal distribution of XA, okay, so the joint distribution of variables in set A, this is still multivariate normal, with which dimension? The number of elements in A, okay, so the sides of the set A, and with mean vector, which is mu A, so the sub-vector of mu with components indexed by A, and variance-covariance matrix, which is exactly the block sigma AA, okay, so the diagonal block that we have here, okay? Okay, so this is very simple. The marginal is still normal, and the parameters of this normal distribution are the 2 blocks, mu A and sigma AA, okay? Okay, so things are a bit more complicated when we consider conditioning, okay? So, and we ask for what is the conditional distribution of XA given XB equal to some XB here. This is a bold symbol and this is not a bold symbol. Okay, I'm not sure you can see the distinction, but anyway. Okay, this is still multivariate normal. Okay, so the multivariate normal is closed under conditioning. Okay, what are the parameters of this multivariate normal? First of all, the sides of this multivariate normal, the dimension is still the sides of set A, and the parameters are what we can call mu A given B and sigma A given B, which have the following expressions here. So still they can be expressed in terms as a function of the elements of those 2 parameters that we have above, okay? Where in particular for the conditional variance-covariance matrix, we have this expression here, which depends both on the block diagonal sigma AA, but also on the out diagonal blocks, sigma AB and sigma BA, okay? So there is this kind of strange relationship between the blocks of sigma and the conditional variance-covariance matrix, okay? And this relationship here is also known as the Schur complement of sigma BB in matrix sigma, okay, which is a more general concept, okay? So something that you can define for any matrix which is partitioned into 4 blocks in a way like the one before, okay? And in the case of variance-covariance matrix has this form here. Have you ever seen anything like that? Have you ever heard about Schur complement of a matrix? Okay, no? Okay, anyway, we have a couple of important results about Schur complements, which are the following that I reported here, okay? So sigma AB, our conditional covariance matrix, is given by this expression, which coincides, interestingly, with omega AA minus 1. So the inverse of the block, the diagonal block of omega, okay, with components indexed by AA. And also, we can write the same by, let's say, exchanging the roles of omega and sigma, which is written here in the second statement, and which is expressing a relationship between sigma AA, so a block of the covariance matrix, and instead the Schur complement of omega, okay, which is the expression reported here. Okay, and this coincides with omega A given B, so the conditional precision matrix, or better, the precision matrix of the conditional distribution of A given B at the -1. Okay, so the two relationships that we have here express a relationship between marginal and conditional covariance or precision matrices, which suggests that when we deal with covariance matrices, okay, like sigma AA, this is useful if we want to establish marginal independencies, right? Two variables are marginally independent if there is a zero entry in the covariance matrix, as we know. While if we want to check, if we want to look for conditional independencies, which is precisely the case in graphical models, it is easier to deal with precision matrices, okay? And so we will see that it is easier to look for not zero entries in the covariance matrix, but for zero entries in the precision matrix, okay? If we are interested in conditional independencies, okay? And these are two very useful results for Gaussian graphical models as well. Okay, so now we would like to write, we will need to write a likelihood function, okay, for a multivariate normal model, as well as then a Gaussian graphical model. Okay, so let's assume that we have some data. So we have n observations, each one corresponding to a vector, xi, with q components. So I will call the elements xi1, xiq, okay? And this is by definition a column vector, okay? And we will assume, as in a very standard setting, that our observations are IID from a multivariate normal model, mu omega -1. Okay, so if this is the case, then we can write the likelihood function as a product I1 to n of the PDF, the probability density function of multivariate normal distributions, one for each xi observation, okay? Okay, and then this can be also written in the form here below, okay? So this will be proportional to the determinant of omega raised at n/2, and then the exp of -1/2, then we can put the product within the exp, which becomes a sum, as you know. So the sum I1 to n of xi minus mu prime omega xi minus mu. Is it okay? Okay. So this is the likelihood function that we will write very similarly even later on for a Gaussian graphical model, where the two parameters are in general our mean vector and our precision matrix. So mu, q1 vector, and omega, our qq. And let me stress from now that omega is not a general matrix. It must satisfy some constraints. And in particular, it must be symmetric and positive definite, okay? Okay, so omega itself has some constraints, even in a general multivariate normal distribution, okay? So still without a graphical model, which will introduce even more constraints on omega. Okay, so just a remark, because typically when we do Gaussian graphical modeling, we are not really interested in the mean vector as a parameter. Okay, we are much more interested in the covariance matrix or the precision matrix, that is omega, because it is the parameter that captures the conditional independence relationships between variables. Okay, so just for simplicity, we can assume that our multivariate normal model has a zero mean. Okay, so something that in practice you can achieve by scaling your variables, by centering your variables, your data, sorry. Okay, and so we can simplify our model by writing the following here. Okay, so a multivariate normal with mean equal to 0 and variance covariance, which is omega minus 1. So if this is the case, we can simplify a bit the likelihood function. Okay, so we don't have anymore mu, which is equal to the null vector. And so the likelihood becomes proportional to omega, the determinant n over 2 exp of what is written there. Okay, and then using also properties of the trace operator, this is a very useful property. The same can be written in this form here as the exp of minus 1 over 2, the trace of S times omega. Okay, and what is this matrix S? Okay, the matrix S is nothing but X prime X, where X is your NQ data matrix. So the data matrix having as the ith row the ith vector. Okay, so old Xi. Okay, so basically this is, if you like, the numerator of the sample covariance matrix if you have the zero mean, right? Okay, and we call this bold S. Okay, so keep into mind this expression here, okay, because it will be quite useful later on, both for frequentist estimation as well as for Bayesian inference, okay? And in particular to structure a conjugate prior for omega. So a prior which at the end gives a posterior which is in the same form. And so the idea is, as usual, to structure it as, say, the likelihood. Okay. Of course, if you have questions, if there is something which is not clear, feel free to raise your hand and ask, okay? Okay, so let me provide you some results also for the Bayesian inference of a multivariate normal model. Okay, so if you want to do frequentist inference, so basically you need to estimate omega, then you can implement maximum likelihood estimation. Okay, in which case the maximum likelihood estimator of omega would be the sample precision matrix, so the inverse of the sample covariance matrix. Okay, so this is very standard. But what about the Bayesian inference of this model? So if you want to do Bayesian inference, we need to assign a prior to omega. Okay, and remember what I told you before, omega has some constraints. It must be SPD, symmetric, positive, definite. Okay, so we need a prior for this parameter satisfying this constraint. Okay, and such prior is the Wishart distribution. Okay, so the Wishart distribution is, if you like, a generalization to a multivariate setting of the gamma distribution. Okay, and is parameterized by two parameters. One is called a shape parameter, A, and the other one is instead a rate parameter, which is a matrix, bold U, okay, and which is itself an SPD matrix. Okay, so in this case, we write that omega has a Wishart Q AU distribution, and its probability density function is given by the expression here. Okay, where the blue term is what is called typically a normalizing constant. Okay, so something which does not depend on omega. Okay, so the black term is instead the kernel of the distribution, and that we can call IAU. Okay, and we will see that this normalizing constant is something which plays a crucial role in Bayesian model selection, while not an important role for posterior inference, at least directly. What about the kernel of the distribution? The kernel of the distribution is quite interesting because it is still the determinant of omega raised at something times an exponential kernel minus 1 over 2, the trace of u which is a matrix, times omega, which is our parameter. So if you compare the kernel of this distribution with the likelihood, okay, you see that basically they have the same structure, right? Okay, and so this suggests that this prior is conjugate. Okay, so if we combine the likelihood with the prior, we will end up with something which still has the same 4, okay, because we have the product of the determinant, so we can sum the two exponents, and then we can combine the trace using properties of trace operator. So we achieve something which at the end is still Wishart with some posterior hyperparameters, and this is enough to say that the prior is conjugate. Okay, is it the first time that you see the Wishart distribution? Yes? No, come on. You attended my course at Bicocca. Okay, so it's not the first time. Ah, okay. You said no. Okay. Okay, for other people, is it the first time that you hear the Wishart distribution? Not the first time, of course. Okay. Okay, so if it is not the first time, pay attention because there are different parameterizations of the Wishart distribution, which instead of the rate parameter, which is what I called U, use the scale parameter, which is the inverse of U. So this is something quite common even in the gamma distribution, where you can parameterize the distribution using the rate or the scale parameter. So pay attention. And one way to check what is the parameterization which has been adopted is to check for the mean of the distribution. Okay. So in my notation, the expectation is A times U minus 1. If instead of the rate you use the scale parameter, the mean would be A times U, okay, without the minus 1. Okay, so pay attention to this distinction. There are at least 2 different parameterizations of the distribution. Okay, so now, if omega is a Wishart with this kind of parameterizations, there are 2 nice properties. So the first one is related to conjugacy. And so if we compute the posterior of omega, which is proportional to the product between the likelihood function and the prior on omega, it is not difficult to see that this is still Wishart with posterior hyperparameters, which are given by A plus n, okay, where n is the sample size, the number of observations, and the posterior rate parameter, which is U plus S. So the prior rate parameter U plus what we called the numerator of the sample covariance matrix, bold S. Okay, so the posterior is still Wishart, which means that if you want to do posterior inference and you have some function, some algorithm to sample from Wishart distributions, you can use it just by updating the hyperparameters and you obtain draws from this posterior distribution. Okay, another important concept in Bayesian inference for graphical models is instead the marginal likelihood. Okay, so what is the marginal likelihood? The marginal likelihood is an integrated likelihood. Okay, so the idea is we start from the likelihood function and we would like to integrate the likelihood function with respect to omega. Okay, so if we multiply the likelihood times the prior on omega, what we obtain is the joint of x and omega. And if we integrate with respect to omega, then we obtain the marginal distribution of x. Okay, so what we can call p of x. Okay, and this will play a crucial role in Bayesian model selection in general, and in particular in Bayesian graphical model selection, more in general. Okay, and another property of the Wishart distribution, of the Wishart prior, is that even this integral here can be computed in, say, a closed form expression as the ratio of the prior and the posterior normalizing constants, which are what we called before IAU, the blue term, which was the prior normalizing constant. And then the same for the posterior distribution, okay, which since this is still a Wishart, we can call I of A plus N, U plus S. Okay, so this is not exactly equal to the ratio of the normalizing constants. There is an extra term here 2 pi raised at minus nq over 2, which comes instead from the likelihood function. Okay. Okay. Then if we write explicitly the prior and posterior normalizing constants, there is something which simplifies. Okay, so this is the reason why you see pi and not 2 pi here, because in the normalizing constant of the Wisher we have this term here as well. Okay, and if you do some calculations, then what you obtain is this expression here. Okay, which again is something that you can compute exactly. Okay, if you set the prior hyperparameters, you have some data so that you can compute S and you have the sample size, you can compute the value of this marginal likelihood. Okay, and we will see that this is useful for model selection purposes in Bayesian graphical modeling. Okay. Any questions so far? Are you familiar with the marginal likelihoods? Have you ever seen anything like that before? Yes? No? Okay. We will go back to the marginal likelihood and to the usage of marginal likelihoods to do Bayesian model selection this afternoon. Okay. For now, it is enough to recall that when we have Gaussian data, Gaussian likelihoods, Wisher priors, we have these closed form results that we will be very useful in the next. Okay, so another very basic model that we need to review is the normal linear regression model. Why? The reason is that we will see that when dealing with directed acyclic graphs in a Gaussian setting, there is a strict connection between Gaussian and what we will call structural equation models, which are nothing but a set of normal linear regression models. Okay, so again, let me fix the notation and let me review some very useful results about normal linear regression. Okay, so we can specify a normal linear regression model in this way by assuming that yi, which is our response variable, given parameters that are parameters that are beta and sigma second are independent, normally distributed with mean, which is given by the linear predictor, beta prime xi, and conditional variance, which is sigma second. Okay. Okay, and now the parameters are beta, which is our p-dimensional vector with our regression coefficients, and sigma second, which is instead the conditional variance, okay, or the variance of the error term, okay, if you prefer another notation. Okay, so if we have a normal linear regression model like the one here under the assumption of independence, then we can write the likelihood function as a product I1 to n of univariate normal probability density functions, where we have in our exponential kernel yi minus beta prime xi, which is our linear predictor, or what you call the residual, right? Okay, and then again, if we put the product within the exp, this will become a sum, okay? And then if we use a bit of matrix notation, instead of the sum of yi minus beta prime xi at the second, we can write it as the RSS, the residual sum of squares, which in matrix notation will be y minus x beta prime times y minus x beta. Okay, so this is the usual likelihood function, where y is now our n-dimensional vector with our n responses from y1, yn, and bold x is still our np data matrix with each row corresponding to one of our n observations. Okay, so the levels of the covariates for subject for individual I. Okay, so this is our likelihood function. Now, again, you know how to deal with normal linear regression in a frequentist setting. Okay, if you want to do estimation of the parameters beta and maybe also sigma second, you can use maximum likelihood and you obtain the popular expression x prime x minus 1, x prime y, even if you use the OLS. Okay, so this is, again, very standard. But what about if you want to do Bayesian inference for a normal linear regression model? So if we want to do Bayesian inference, again, we need to set a prior on the parameters, which are beta and sigma second. Okay, so even in this case, we have a conjugate prior for our parameter, beta sigma second. And if we want to achieve conjugacy, we need to structure the prior in the following way here. Okay, so the joint prior must be written as a product of a conditional prior, P of beta given sigma second, and the marginal prior for sigma second. So we must introduce, let's say, dependence from sigma second in the prior on beta, okay, in a sense. Okay, and the distribution of beta given sigma second should be a multivariate normal, okay, with dimension p. Remember that beta is p-dimensional, with some prior mean that we can call beta 0, and some prior variance covariance matrix, which depends on sigma second. So here it is the dependence on the other parameter, sigma second, times v minus 1, which is something playing the role of the variance covariance matrix. So V is something like the precision matrix, okay? What we called omega before. Okay, so a multivariate normal prior for beta, which makes sense. What about sigma second? Sigma second must be positive, okay? So we can assign to sigma second a gamma or even an inverse gamma prior with parameters that you can call A and B, or just to ease the notation in the posterior distribution, I will parameterize it as 1 half A, 1 half B. Okay, but you can call them whatever you like. You still achieve conjugacy. Okay. Okay, so we know what is the PDF of a multivariate normal distribution. So for the conditional prior on beta, so I will not write it again. What about instead the prior on sigma second? This is an inverse gamma that you can write, for which you can write the PDF in this form here, okay, where still we have some normalizing constant, which is the blue term, depending on our prior hyperparameters, 1 half A and 1 half B, and that we can call CAB. And then we have the kernel of the distribution, okay, which is the black term depending on sigma second. Okay, so the term that you have here. Okay, another way to say the same, which was written here, is that the vector parameter beta sigma second has a normal inverse gamma distribution, which means that the conditional of beta given sigma second is multivariate normal and the marginal on sigma second is instead inverse gamma. Another way to say the same is that the joint is normal inverse gamma. And as such, this is a prior. It will have its normalizing constant, which will be the blue term for sure, and then something more coming from the multivariate normal prior, okay? The normalizing constant of the multivariate normal prior on beta, okay? But I will not write it explicitly just for simplicity. Okay, so properties of this prior, of this conjugate prior. Of course, the posterior is still multivariate normal inverse Wishart, okay? And it will be a multivariate normal inverse Wishart with the parameters that I will index with this tilde symbol here. So we can write that beta, given the data, okay, as well as sigma second, is still multivariate normal P with a posterior mean beta tilde and a posterior precision matrix, say, which is V tilde instead. And then similarly for sigma second, we have the same as before with updated hyperparameters. So instead of A and B, we have A tilde, B tilde. And all these posterior hyperparameters have an expression, which is summarized here. Okay. So for example, you can recognize in beta tilde an expression which is very similar to the OLS, right? Okay, because you have x prime x minus 1 here, you have x prime y. The only difference is that you have the prior as well. And so you have plus something coming from the prior, V and B0, which are the prior hyperparameters, okay? But something which is still very related to the OLS estimator or the maximum likelihood estimator of beta. And then you have a posterior precision matrix, which is V plus what we called before S, X prime X, so something which is familiar, and something which is a bit more complicated for the two parameters of the inverse gamma, not for the first one, A tilde, but for sure for the second one, which has this expression here, but we can forget about it. Now, the important point is that the posterior is still multivariate normal inverse gamma, so if we want to do posterior inference, we can sample from using a Monte Carlo strategy from the inverse gamma posterior of sigma, then we plug in the multivariate normal posterior and we sample from it. And in which case we obtain a joint sample from this posterior distribution, okay? As in Monte Carlo estimation in Bayesian inference. Now, the second important property is related again to the marginal likelihood, which is still available in closed form. So now, if we call IABV and I, A tilde, B tilde, V tilde, the prior and the posterior normalizing constants, okay, then it is possible to show that the marginal likelihood of a normal linear regression model is still available as a ratio of prior and posterior normalizing constants. Okay, and this is the result that I tried to summarize here. So let's start from the definition of marginal likelihood, okay? So again, we start from the likelihood, okay, which is what we wrote as P of y given beta sigma second. Then again, if we multiply this by the prior, P of beta sigma second, we obtain the joint. And if we integrate with respect to our parameters, beta and sigma second, what we obtain is the marginal distribution of our data. Okay, so the marginal data distribution or marginal likelihood, P of y. Okay, and again, it is possible to show that this integral here can be solved in a closed form expression, which depends on the prior and the posterior normalizing constants. So again, what I called IABV, which is the prior normalizing constant from the prior normal inverse gamma, divided by the posterior normalizing constant, the red term, I, A tilde, B tilde, B tilde. Okay, and then if you write explicitly those normalizing constants, you will obtain something like what I reported here, okay? That you can see it is very symmetric because you have all the same terms, but once with V, the other time with V tilde, once with A, the other time with A tilde, okay, since you have both the prior and posterior normalizing constant. Okay, so apart from the result here, the nice thing is that you can compute it whenever you have some data and you have fixed some prior hyperparameters, A, B, and V. You compute the posterior hyperparameters and then you have a number for this marginal likelihood here. So something that you can compute. Okay, we will see that this is particularly useful for DAG model selection. Okay, when we will approach DAG model selection through a Bayesian framework. Okay. Okay. So now we would like to extend, or at least to start by extending these results to graphical models. Okay, so from standard, say, multivariate normal and normal linear regression to Gaussian graphical models. Okay, and we will consider both the case of an undirected graph and the case of a directed graph. Okay, so let me just summarize a bit a few notions on undirected graphs that you introduced yesterday, and in particular, how to read conditional independencies in a graph, because we would like to establish then a connection between the graph and the multivariate normal distribution, okay? So how can we read from the distribution, the conditional independencies in the graph and the converse as well? Okay, so remember what you said yesterday. If you have an undirected graph G, okay, this is a pair VE, with a set of vertices and a set of undirected edges, such that if we have UV, we also have VU, okay? So equivalently, we can say that the adjacency matrix of this graph is symmetric. Okay, now remember separation in an undirected graph. If you have three disjoint subsets of the set of vertices, say A, B, C, then we say that A and B are conditionally independent given C if A and B are separated by C in the graph. And what does it mean? It means that all paths from A and B, namely from vertices that are in A and vertices that are in set B, must go through elements that are in C. Okay. Okay, so just as an example, here we have that 5 and 2 are independent given 3 and 4, because if you want to move from 5 to 2 or from 2 to 5, you must pass through 3 and 4, right? Okay, so there is no path which avoids to go through 3 and 4. Okay, and similarly, we can say that 1 and 5 are conditionally independent given 2, 3, and 4, but even simply given 2, because you must pass through node 2 if you want to move from 1 to 5. Okay. Okay, so this is how we can read conditional independencies using separation in an undirected graph. Okay, now, in an undirected graph, we have that a missing edge between two nodes, in particular, implies that U and V, these two nodes, are conditionally independent given all the remaining variables nodes. Okay, probably it is enough to condition on a smaller subset. Okay, as we wrote here, for example. Okay, so 1 and 5 are just simply independent given 2, but for sure we can say that if there is a missing edge between nodes U and V, then these two are independent conditionally on all the remaining nodes. Okay, and this is something that we can write in this way here. Okay, U independent of V given V minus U and V. Okay, so now the question is, how can we translate this into a Gaussian graphical model, or at least into a Gaussian, multivariate Gaussian distribution? Okay, if we assume that x1, xq has a multivariate normal distribution, okay, with, for simplicity, 0 mean, then what happens is that xu and xv, so the two random variables now, are independent given all the remaining ones, okay, so what I call x sub v minus uv, if and only if the uv entry, the uv element, the element at position u and v in the precision matrix omega is equal to 0. Okay? So I will not give you a proof of this result, but if you are interested in a proof, you can refer to the Handbook of Graphical Models. In chapter 9.1, there is a proof of this statement here. So the important thing to our purposes is that in a Gaussian graphical model, then 0 entries in the precision matrix corresponds to conditional independencies of this form here. Two nodes being independent given all the remaining ones, which is exactly the kind of conditional independence that we can read using separation in the Markov property of an undirected graph. Okay, so what is the implication of this result here? The implication is that in a Gaussian undirected graph model, we can learn a graph by estimating what we call a sparse precision matrix, which means a matrix containing 0 entries, okay? And one possibility is to encourage 0 entries in omega. And whenever we find a 0 entry in omega, by applying some kind of statistical methodology, then we can say that there is a missing edge between U and V in the graph, okay? Okay, so equivalently, graph estimation can be performed through sparse precision matrix estimation, okay, by estimating a sparse precision matrix, that is, by encouraging 0 entries in the precision matrix. Okay, so finally, how can we write a Gaussian undirected graphical model? We can write a Gaussian undirected graphical model in this way. We start from an undirected graph G, and then we assume that the joint of x1, xq is multivariate normal 0, omega minus 1. But now we ask to omega to be not only symmetric and positive definite, but to satisfy the conditional independencies encoded in the graph. Okay, and this is something that we can write using this notation. We ask to omega to belong to this space PG, okay, which is the space of all symmetric, positive, definite precision matrices that are also Markov with respect to an undirected graph G, okay, which means that it must satisfy the 0 entries whenever there is a missing edge in the graph. Okay. Okay, so this is how in general we can write a Gaussian UG model. Okay. Okay, so let's move to directed acyclic graphs instead. And again, let me just recap a few notions about conditional independencies in directed acyclic graphs. Yes. Yes. Okay, you have to think of it is a cone, okay, for a matrix. Okay, so omega is let's say a random matrix. Okay, which will lie in some space. If you consider the bivariate case, of course, it is easier to see it. So it is a multidimensional space. All these matrices in this space must be symmetric, positive, definite, and this is enough. But they must have 0 entries whenever there is a missing edge in the graph. So all these matrices must have a 0. Okay, so like, let's say a point mass at 0 at position u and v if in G there is a missing edge. So assume that G is fixed. So the graph is telling you that there must be some zeros in some components of omega. So all these matrices in this space must have exact zeros, so sort of degenerate distributions at those positions, corresponding to nodes, coordinates, for which there are missing edges in the graph. No. No, because the element itself of an omega entry, okay, of course, all omega is a random variable. Okay, so you have the non-zero elements of omega maybe in a set which is between 0 plus infinite, right? Okay, think of the, I don't know, gamma distribution for simplicity, okay? So it is defined over a set of positive integers, not integers, real numbers, okay? So you have many possible realizations of the variable itself, okay? So for some elements, you must have the 0. And for the other ones, it may be 0.1, it may be 10 or whatever, okay? So it is still a random variable, but with some restrictions, which are elements that are exactly equal to 0. But for the other elements, you don't know the specific value, okay? The graph is just telling you what are the zeros, but nothing about the other entries, say. Okay. Okay, so what about directed acyclic graphs? So we start from a DAG, which is again a pair, V, E, with a set of vertices and a set of now directed edges, which implies that if we have UV in the set E, then we don't have VU, okay? So in this case, the adjacency matrix of the graph is not symmetric anymore, okay? it is not required to be lower or upper triangular. So, but in any case, if you have a UV entry equal to 1, then you cannot have the converse, okay? Because you don't have bidirected edges. Okay, so for DAGs, probably you mentioned yesterday, there are several criteria to read conditional independencies. One is the separation, which was introduced by Pearl. The other one is instead based on the moralization criterion, which is still based on separation, on the notion of separation in an undirected graph, which is not the undirected graph that you obtain by disregarding the edge orientations, but what is called the moralized version of a DAG. Okay, so if you want to know more, the book by Lauritzen is a good reference for this. Okay, so in particular, among all possible conditional independencies that you can read from a DAG, let me just recall one which is quite useful. We have that a node variable is independent of its non-descendant given its parents. So what are the non-descendants? Basically, they are all the nodes that precede the parents in the ordering that you obtain by following the directed edges, okay? So for example, for node 5, 2 is a non-descendant and 1 is a non-descendant because the parents are 4 and 3, okay? And so this is something that we can write in this way here. V is independent of its known descendant, okay, given its parents. Okay, and for example, if we look at the directed graph here, what we have is that 2 and 5 are independent given 3 and 4. 3 and 4 are the parents of 5, right? And 2 is a non-descendant of 5. And similarly, we can write that 6 and 4 are conditionally independent given 5, where 5 is a parent of 6 and 4 is a non-descendant of 6. Okay, now another important feature of DAG models is related to the DAG factorization, that if you remember, under some conditions implies the global Markov property of the DAG, okay, which is what at the end we would like to have. Okay, and this will be very useful for structured learning purposes, as also you for sure said yesterday. Okay, so if we have x1, xq random variables and we have a DAG, then the DAG factorization can be written in the following form. Okay, so the joint distribution of x1, xq can be written as a product j1 to q of conditional distributions of this form xj given x parents of node j in the DAG. So basically is a product of conditional distributions saying that the node j only depends on the parents, okay? Okay, and if, for example, you take the DAG here, then you can factorize the joint in the form that it's reported here, okay? As a product of 6 conditional distributions. Okay, and then what I said before, remember that the factorization property, so whenever you can factorize a joint distribution under some assumption, like the normal assumption, in this way here, then the global Markov property of a DAG is guaranteed, provided that F has some properties, and notably a strictly positive support, which is guaranteed for Gaussian graphical models, okay? So for Gaussian DAG models, we will rely on the factorization, on the DAG factorization, in order to establish a connection between the multivariate distribution and the DAG itself. Okay. Now, before moving to the definition of a Gaussian DAG model, let me just recall you a few more concepts related to DAG Markov equivalence, okay? So you know that there may be DAGs that are different because they are structurally different, like D1, D2 here, which are different because of the orientation of an edge, which is between 1 and 2, okay? And if this is the case, then they will imply different factorizations, right? In one, you will have the conditional of 2 given 1. In the other one, you will have 1 given 2. Okay? But if you read the conditional independencies from these two DAGs, using this separation, using the other criterion, or whatever you like, you will discover that the set of conditional independencies encoded by the two DAG are exactly the same. Okay? And also, if you read the same from the factorization of the joint distribution, again, you will see that there are exactly the same conditional independencies. So in this case, we say that the two DAGs are different yet, but they are Markov equivalent because they have the same Markov property. Okay, so another way to express the same is that in practice, they represent the same statistical model because they imply the same set of conditional independencies. And this is an important aspect that we must care about in score-based model selection methods, both frequentist but also Bayesian. And the idea is that if you want to assign a score to DAGs, you must guarantee that if two DAGs are equivalent, they must have the same score. Okay? So in terms of likelihood, this is, let's say, trivial. We said before, the two likelihoods are equivalent because the two statistical models are the same. But if you think of a Bayesian approach, for example, and you need to assign a prior to the parameters, and the two parameters are different because in one case you have a conditional parameter or the parameter of one conditional distribution, in the other case of another conditional distribution, you must care about this feature if you want to achieve score equivalence, which means in a Bayesian setting, same marginal likelihood, and in turn, same posterior probability for the two DAGs. But we will go back to this concept. Just remember this notion. And another notion that I just want to recap is the one related to a representation of a Markov equivalence class of DAGs. Okay, so there are criteria also to establish if DAGs are Markov equivalent. And one possibility is to check for the skeleton, so the underlying undirected graph. So what you obtain if you don't care about the orientation of the edges, and the set of V structures. You remember what a V structure is? Yes? Yes or no? Yes. Okay, so what is a V structure, for example, which is common to D1, D2, and D3 here? One? 1, 2, and 4, this one, you mean? This is structure because there is 1, 2, 2. So for this structure, you must have a structure of this form here. Okay. Right? Where U and V are not connected. Okay. So in this case, the V structure is 2, 3, and 4, right? Because 2 and 3 are not connected, and they both point to 4. You agree? Okay. And D1, D2, and D3 all have this V structure, you say? Okay. Okay, here and here. Okay, so there are no other V structures. Okay, you can check, but there are no other V structures. And they have the same skeleton. Okay, but if you don't look at the orientations of the edges, they have the same skeleton. Okay, it is possible also to show that there are no other DAGs that have the same feature. So other DAGs with same skeleton and same V structure. You need to reverse some edges and you introduce cycles, for example, and this is not a DAG anymore, or you need to remove a V structure and then you fall outside the equivalence class. So in other terms, these three DAGs represent an equivalence class. They are equivalent, yes, and there are no other DAGs that are equivalent to them. Okay, so this suggests that the space of DAGs can be partitioned into Markov equivalence class. So instead of considering DAGs, you can consider their Markov equivalence classes, and this is not enough. You can also represent each Markov equivalence class using an object which is still a graph, but it is not a directed graph anymore. It is a partially directed graph, which is called the essential graph, or also completed partially directed acyclic graph, CPDAG, okay? And this is particularly common in the machine learning community, right? While essential graph is more statistical. It was introduced by Anderson, Madigan, and Perman in a paper at the end of the 90s. Okay, so how can we build this essential graph? So basically what we need to take is the union of these three DAGs. What do we mean by the union? Is the union with respect to the set of edges, okay? And if you remember how we define the set of edges as a set of ordered pairs, UV belonging to E, whenever we have both UV in one DAG, and then we have VU in another one, if you take the union, we end up with an undirected edge, right? UV and VU, okay? Okay, so this is the reason why in this essential graph we have some undirected edges. But we may have edges which always have the same orientation in all DAGs within the equivalence class. For example, those that are involved in a V structure, 2, 3, 4, okay? They always have the same orientation. So even if you take the union, you will end up with directed edges. And there may be other edges, like 1, 4, that even if not directly involved in a V structure, for some reason, we will go back to this reason later, they always have the same orientation. 1, 4 is an example, and then you have 1, 2, 4 in the essential graph as well. Okay, so this essential graph is a partially directed graph. And why we need essential graphs? Because there are some score-based methods that say, okay, instead of working on the space of DAGs, since some DAGs are equivalent, okay, do not repeat the analysis for DAGs that are the same, okay? Save time, for example, and consider the space of Markov equivalence classes or the space of essential graphs. So the representatives of these Markov equivalence classes. Okay, and this is one reason. Another reason is more from an interpretation point of view. If you have a score method which outputs a DAG estimate, you must be careful, okay? Because it may be that some edges in the DAG that you have estimated, okay, have some orientation because you used a DAG score-based approach, but the orientation of those edges is not unique because there might be another DAG which is Markov equivalent with the orientation which is the reverse for some edges, okay, for example. So instead of looking at the DAG estimate, you may want to reconstruct the representative essential graph, which is basically saying, I cannot determine the orientation of these edges, okay? So I estimated this DAG, but the orientation is not unique in the equivalence class. Okay. So for the first reason that I mentioned before, an example of methodology working directly on the space of equivalence classes is the so-called greedy equivalence search, which has been introduced by Chickering, okay, in 2002. Okay, but then there are also Bayesian methodologies. We will mention something in the next sessions of today's lecture. Okay, so now finally we would like to define a Gaussian DAG model, okay? So how can we define a Gaussian DAG model? We can start by saying something similar to what we said before for undirected graph. We have a DAG, DVE, and we assume that the joint distribution of our random variables is multivariate normal, 0, omega minus 1, and we now ask to omega to satisfy, to be SPD, okay, but this is the standard, but also to satisfy the conditional independencies encoded in a DAG now, okay? So accordingly, in this notation, PD is the space of all symmetric, positive, definite precision matrix, but which are Markov also with respect to a DAG D. Okay, so now the question is, how can I establish the connection between the constraints on the parameter of this model, for example, omega, and the conditional independencies in the DAG, for example, the missing edges between two nodes. Okay, this is not easy to achieve by considering this parameterization in terms of the precision matrix. If we want to establish a connection between constraints in the parameters and missing edges in the DAG, we need to rely on another parameterization, which is based on the so-called structural equation model representation of a Gaussian DAG model. Okay, so what is a structural equation model representation? Okay, so basically it is a set of linear equations, okay, where each equation refers to one variable, okay, and as we will see, it corresponds to a normal linear regression model, okay. So instead of looking at the joint, okay, you can specify a model by writing the conditional distributions node by node, okay, and because of properties of the multivariate normal, the conditional distributions are still normal. If you look for univariate, they will be univariate normal, and there will be similar to, say, normal linear regression models. Okay, so in general, we can write a structural equation model using this kind of notation here. So we write X, which is our Q1 vector, equal to a matrix B prime, which is a Q times Q matrix, as we will say, of something like regression coefficients, times X, so our Q1 vector, again, plus an error term, which is a vector, okay, again, and which is multivariate normal, 0, D. Okay, so the error term now is a matrix. The components of this vector are independent because we ask to D to be diagonal with entries equal to D11, DQQ, the diagonal entries of this matrix here. Okay, so if you write explicitly this, you will have a system of linear equations, x1, xq, a matrix B times x1, xq plus epsilon y, epsilon q. Okay, and what we have inside B is a collection of regression coefficients, okay, such that, remember the DAG factorization. In the DAG factorization, each node depends only on its parents, okay? So accordingly, in B, we have a UV element if and only if we have an edge from U to V, okay? Because V depends from U, which is a parent of V. Okay, now if we want to establish the connection of between this new parameterization, D and B, and omega or sigma, we can compute the variance of our random vector X. Okay, so one possibility is to write first I minus B prime. Okay, in this way here. And then what we can do is to compute the variance of X. Sorry, here we don't have the -1. Okay, and if we apply the variance operator to X, okay, here the only random variable is epsilon, right? And because of properties of the variance operator of a linear combination of random variables, we obtain this result here, okay? Saying that the relationship between sigma and D and B, our two new parameters, can be written in the following form here. And similarly, if you take instead the inverse of sigma, which is the precision omega, what you obtain is instead the relationship between here. So basically, we are using a reparameterization of the precision matrix in terms of two new parameters that are a matrix of regression coefficients and the matrix of conditional variance. Okay, and the reason is that we would like to exploit the DAG factorization, okay, which is possible, as we will see, using a structural equation model. Okay, and also we would like to read conditional independencies through 0 elements in some parameter, and this parameter is the matrix B, okay, our matrix of regression coefficients. Okay, but this is simply another way to parameterize omega, which is given by this relationship here. Okay, this is sometimes called modified Cholesky decomposition, okay, if you know if you are familiar with Cholesky decomposition of covariance matrices. Okay, so now what I was saying before is that under the structural equation model representation, the distribution, the conditional distribution of each component of our random vector, that is xj, is that of a linear regression model with regression coefficients corresponding to the elements of our matrix B, with rows indexed by the parents, okay, the set PAJ, and the column corresponding to the node J itself. Okay. Okay, what are the elements playing the role of the covariates for xj? They are its parents. Okay, so variables in the set x PAJ plus an error term, which is epsilon j, the jth component of our epsilon vector, which has a marginal normal distribution 0 djj. Okay, so if you look at this structure here, then what you see is that basically the distribution of xj is that of a univariate normal distribution with a mean which is given by a linear, say, predictor, okay? So something like beta prime x, and a conditional variance, which is djj. Okay, so something which looks like a linear regression model, okay? And we know how to deal with linear regression models, both in frequentist estimation, but also in Bayesian inference, okay? We know which prior to assign to B and djj, for example, multivariate normal, inverse gamma. So we know to achieve how to obtain posterior distributions in closed form, marginal likelihoods, and so on. Okay, for now, what we are more interested in is to write explicitly the DAG factorization under the Gaussian assumption, okay, which is written in the following form here. So the joint distribution of x1, xq, given the parameters, which are now b and d and not omega anymore, can be written as a product j1 to q of q normal densities, okay, where dn stands for the PDF of a univariate normal, where the mean is b prime elements parents j times x parents j, and the variance is instead djj. Okay, so what appears from this expression is that each xj only depends on its parents, okay, as in the DAG factorization. So accordingly, what we have is that only elements corresponding to the parents of J in the DAG are different from 0, okay? So again, the UV elements of B are different from 0 if and only if we have an edge from U to V, okay? Okay, so for a Gaussian DAG model, missing edges in the DAG will correspond to 0 entries in the matrix B. Okay, so before looking at some R code in the last part of this lecture, let me just give you some references. So if you're interested in some results on multivariate normal distributions, the book by Press is the right reference. So what I mentioned at the very beginning of this lecture. While if you are more interested in an introduction, but it is with much more than an introduction, for example, proofs related to conditional independencies in Gaussian graphical models that I mentioned before, the handbook edited by Matuis and co-authors is the right reference. Then we have the book by Lauritzen and even the one by Cowell, David Lauritzen. Probably it is a bit more user-friendly. The first one are good references for an introduction to graphical models and Gaussian graphical models also. Okay, so in the last part of this lecture, I just want to show you something which will be useful even for the next parts of the lecture. And in particular, I would like to show you how to simulate some multivariate, some data from a Gaussian graphical model. Okay, so multivariate normal data, but from a graphical model. Okay, so there are some libraries that you will need to install, but for now it is enough the MVT norm library at the very end. The other libraries will be useful for frequentist estimation in Gaussian graphical models, but we will use them later on. Okay, so what I would like to do now is to simulate some data from a Gaussian graphical model, and I will consider a Gaussian DAG model for simplicity. Okay. Okay, so I will exemplify this with a very simple example. So in practice, you have data. Okay, you don't need to simulate data, but just as an exercise, I think this can be useful, even if you want to check if the method that you implement works and can identify the true DAG. So if you know the truth because you have simulated the data, then you can use it as a benchmark to evaluate the accuracy of your model. Okay, so I will fix the number of variables, the number of nodes as 6. So Q is equal to 6. Okay, and I will start by constructing the adjacency matrix of the DAG. Okay, so let me call this matrix A, and then I will fix the entries as 1, okay, for these coordinates. Okay, for example, 2, 1, 3, 2, and so on. Okay. Okay, so at the end, this is the adjacency matrix of my DAG. Okay, there are several libraries that can be used to plot a DAG. The one that I need here is provided by the PCArg package. So if you just want to plot the DAG, you need to load, perhaps to install the package first, and then you can do the following. Okay, so I need to create an object, which is an object of class GraphNL. Okay, so I need to convert the adjacency matrix into a GraphNL object. Okay, and if I do this, then what I can do is to plot, okay, the DAG, and this is the DAG that I generated. Okay, is it okay? Okay. So later on, we will also need to consider the representative essential graph. Okay, so this is possible using a function which is called DAG to essential graph. Okay, which applies again to an object of class GraphNL. Okay. Okay, and if you plot both graphs in the same plot here, what you obtain is these two objects. Okay, where you see that the first one is the directed one. The second one is instead partially directed, or in this case, it is undirected, where undirected in this package means that you have the orientation in both directions. Okay. Okay, and also let me stress that this is also an undirected graph. Okay, so basically the data that we are going to generate to simulate can be used at least both for DAG estimation and UG undirected graph estimation. Okay, because the truth belongs both to the space of DAGs and to the space of undirected graphs. Okay. Okay, this is even a decomposable graph, okay, which is Markov to some DAG. So, okay, I did it intentionally, of course. Now we would like to generate some data, which means that we need to fix the parameters of our DAG model. Okay, and the parameters of our DAG model are what we called capital B and capital D, a matrix of regression coefficients with U, V entries different from 0 whenever we have an edge from U to V. Okay, so one possibility is to take the adjacency matrix, which is the matrix with the right 0 entries, the 0 entries at the right position, and then, for example, multiplying by some R-unif draws, okay, draws from a uniform distribution, which will be our regression coefficients. Okay. Okay, and this is what we obtain, for example, okay, the weights of our edges, if you like, or our regression coefficients. While for the matrix D, the matrix with the diagonal entries corresponding to the conditional variances in the structural equation model, we can fix equal to the diagonal matrix, okay, to the identity, just for simplicity. Okay, now if we want to simulate data from a Gaussian DAG model, so basically we need to simulate multivariate normal observations, okay? And you can use packages like the package mvnorm. Okay, the only problem is that when you use mvnorm, the parameterization is the one corresponding to mu and sigma, okay? So we need to use what we wrote before, the relationship between sigma and d and b, okay? So before applying our mvnorm, we need to compute sigma, our variance covariance matrix, simply by doing this kind of computation here, okay? While for the mean vector, we assume for simplicity that it is a zero mean multivariate normal, so we can fix it equal to zero, a vector with with q0 entries, mu. Okay, so this will be our mean vector. This will be instead sigma I minus b prime at the -1 times d times I minus b prime at the -1 transposed. Okay. Okay, you can also recover omega, for example, okay, by doing the solve of sigma. And let me just show you what we have in omega. Okay, remember what I told you. Even if we are simulating from a DAG, this is equivalent to an undirected graph. And if you look at the structure of omega, what you have is exactly that kind of sparse structure that we mentioned before, with zero entries corresponding to missing edges in the undirected graph here. Okay. Okay, so finally, let me simulate our Gaussian data. Okay, I will fix the seed, okay, like 1, 2, 3, and I will apply the function rmvnorm for a number of draws equal to 1000, for example, setting mean equal to mu and sigma equal to the variance covariance matrix that we computed before as a function of b and d. Okay, and these are my data from a Gaussian DAG model. Okay, so something to which we will apply some structured learning methods, and then if we are lucky, what we will recover as a DAG structure or a UG structure will coincide with the true one, with the true graph that we use to generate the data. Okay, the sample size should be large enough to have this kind of, let's say, consistency result. Okay, do you have any question till now? Any curiosity? Feel free to ask if you have. Okay, so if not, I think we are in time for our break, and then we start again at 11.